A very good afternoon, everyone. My name is Raghav Garg, and today I'd like to have a discussion on simulating acoustic environments using convolutions in music productions and synthesis. This is my presentation for PHN 313 Signals and System. First, I'd like to start my discussion with a brief discussion on convolutions. What are convolutions? In its essence, a convolution is a mathematical function that is used to describe the overlap between two functions. In graphical form, it may look something like this. Here are two functions shown in red and blue, and as the area overlap between them increases and decreases, the output function, which is the convolution of these functions, increases and decreases as shown. Now, in mathematical expression, it may look something like this. It is described using an asterisk between the two functions f and g. Now, if we are to find the convolution between function f and g, we will first take the function g, reverse it, then to find the convolution up to time t, we will convert g to gt minus tau, multiply it with f tau, and then take their sum from minus infinity to infinity. This will lead us to the convolution of these two functions. Now, for in a real life scenario, it may look something like this. Say for an hospital, it has a dedicated plan for each day of the week for different patients. The patient count is given as 1, 2, 3, 4, and 5, and as we convolute between these two lists, we can get to the daily usage or the daily load on the hospital. This is how convolution work. Now, the next tool in our study of applications of convolutions in audio processing is impulse response. As the name suggests, impulse response is the output of a system of an LTI system which is provided with a brief input signal known as an impulse. Impulse response generally looks something like this, though in an ideal scenario the time duration tends to 0. Now, an interesting property of an impulse response is that an impulse response of a system carries properties of the system. That is, when an impulse response of a system is convoluted with the signal of another system, the signal is modified as per the impulse response. Therefore, impulse response measurement is an important study. Now, impulse response is not direct, though an impulse response exists in the time domain, it is not directly measured. It is rather measured in the frequency domain, which can be then converted to the time domain using inverse Fourier transform. Although, in fact, with a time domain measurement of an impulse response, what you measure will always be band limited, and thus such responses are measured in the frequency domain and then converted to time domain. We then lead to a very interesting property, which is what happens when we convolve an impulse response of one system with another signal. Mathematically, say we have two functions xt and del t minus 1 showcasing our impulse response. Yt is our output function, which is the convolution between these two functions. Once we apply the convolution between these two functions, our output function yt looks something like this, which is a bit modified as per our impulse response. Mathematically, it looks something like this. Xt convolution with del of t minus 1 is equals to x of t minus 1, which in general sense is xt convoluted with del of t minus beta is equals to x of t minus beta. Graphically, or as in signal processing, our convolution will look something like this. Say we have a signal which is a sawtooth signal, which is quite famous, and an impulse response which looks something like this. When these two functions are convoluted, we get to an output signal which will look something like this. Now clearly, this is of the form of the sawtooth signal, which is modified as per our impulse response. Clearly, there are changes in our sawtooth signal and is in a form modified as per our impulse response. Next up, now convolution of impulse response with signals has some very interesting applications in the process of music synthesis. How so? Impulse response captures the acoustic signature of a physical space or reverb unit, as in, for example, we are in a setting of a concert or we are in a setting of a cathedral. The impulse response of these two settings would be quite different as these are different systems. Next, the convolution process. Now this is important. When you convolve an audio signal like a dry vocal which is recorded in a studio environment with an impulse response of another environment, it makes the signal sound as if it was recorded in that specific environment. Or we can say that the signal has been modified or the impulse response transfers its properties to our audio signal. For example, convolution of an impulse response recorded in an acoustic environment simulating a concert with a guitar tune played in a room leads to guitar sounding as if played in the environment itself. That is, earlier our guitar would sound very dry and free from any noise since it was recorded in a room setting, while our impulse response is recorded from a concert hall. Now, when these two audio signals are convoluted, we get to an audio signal that sounds like our guitar signal but in a concert environment. That is, the concert environment properties are transferred to our guitar signal. Here, let us show a live demonstration of this. Now, as we can see, the first signal is a guitar signal recorded by me in my room, a very short audio. Now, the second audio is a concert IR, concert impulse response that I have downloaded off the internet, which is of a Vienna concert hall. When we convolve these two audios, we get with this audio. As as can be heard pretty clearly, our guitar audio now sounds something as if recorded in a hall. This is due to the convolution of our guitar audio signal with the concert impulse response. Hence, our convolutions showcase their physical importance by convoluting a audio signal with the impulse response leading to a convolved audio which has the properties of the impulse response while maintaining the basic theme of our original audio. In the form of graphs or signals, it looks something like this. This was our original guitar audio signal as recorded by me in my room. This is which is when convoluted with our impulse response recorded in our concert hall setting results in a convolved audio signal. As can be seen, this is our original audio and this is our final audio which has some modifications as per our impulse response audio signal. Now this property has multiple use cases and is used during multiple scenarios in music production and synthesis. For example, the first one is different acoustic environments. For our audio which is recorded in a studio environment can be shown as to be recorded in different acoustic environments such as recorded in a cathedral hall or recorded in a concert or recorded in natural environments so and so. Second, it is used to add realism to our studio recording. During music production for movies, adding realism to our audio is very important to set up an environment for our audience. Third, it is used to create modulated audio, as can be seen. And fourth, and also multiple properties can be added to our audio signals such as reverb or realism, and and it can be used to change recording setup from one place to another using the impulse property of different scenarios. Okay, now let's come to the challenges that come with convolution of impulse response to change the properties of our audio signal. The first one is computational load. Now, since our audio signal is processed at each time interval, it from minus infinity to infinity, or for the entire duration of audio signal, it is extremely computational loading, heavily computational loaded, since it can become very expensive for each point to convolve each point for during the process. Next, now this computational load leads to a latency in our system. This can be very demanding and can lead to real life obstructions when applied in real time. For example, in concerts when the singer is performing and we need to produce an output signal, this can lead to a delay or a latency. Now, how do we solve these challenges? There is a very basic method that we can apply to overcome these challenges or at least mitigate them. This method is the fast Fourier transform or FFT. Fast Fourier transform is an algorithm that is used to transform signals to the frequency domain using Fourier transform for more efficient processing. Since in time domain the convolution is very computationally expensive, while in frequency domain we can convolve with much less compute power required. How this helps us in our processing is, first, it reduces our time complexity from O of n squared to big O of n log n. Since in earlier time domain convolution, each point of our audio signal is multiplied with each point in our impulse response, leading to an time complexity of big O of n square. While in fast Fourier transform, this compute power is mitigated by to big O of n log n, hence reducing our computational load. Second, fast Fourier transform algorithm breaks down the audio into smaller chunks or frames and then processes them independently. This further leads to smaller compute required and thus helps in reducing latency as well. Third, fast Fourier transform algorithm helps us in finding a good balance between processing speed and its efficiency. This is very useful in real-time scenarios where even a minor delay can lead to a performance becoming very stale. Thank you. This was my discussion on use of convolution in real time. Convolution of audio signals with impulse response in real time for music process production and synthesis.